this is the energy generation use breakout session. My name is Liam. I work with ETP, and I'll be chairing today's session. So yeah, we've got a great lineup of speakers ahead, and kind of mix of early career researchers who have started their own independent groups, as well as some PhD students who are, and we'll hearing about their day-to-day work in the lab. And the range of science will be relatively broad, but we'll be hearing about solar PV, some perovskite solar cell talks, as well as some energy storage, hydrogen generation, as well as some carbon capture and storage. So very broad, I guess, a lot to sink your teeth into. So just a couple points to note, I guess, please put your questions in the discussion forum at the bottom of the page, and the speakers will be kindly hanging around the networking area after the session ends. So please use the opportunity to introduce yourself, go talk to them, hear about their work. Okay, so I'll get on to the talk. So the first speaker is from the University of St Andrews, Dr. Lethy Krishnan Jakadama. So I know Lethy quite well. I guess we used to collaborate together during my time as a PhD student. I took a lovely placement to her group, and she taught me how to make organic solar cells. I guess if anyone likes some bedtime reading, there's a lovely paper from 2018 featuring Lethy and McCarran et al. I'll leave it out there. Okay, so following Lethy's work in organic solar cells, she moved into the emerging field of perovskites, first as a Marie Curie research fellow. Then in 2020, she started the Energy Harvesting Research Group at St Andrews as a UKRI Future Leader Fellow. It's a very prestigious award, so it's great. And today she's going to speak to us about some of this energy harvesting properties, in particular indoor light harvesting of halide perovskites from the perspectives of device architecture, photoactive perovskites, and measurement approaches. So thank you, Lethy. Over to you.
Okay, thank you so much, Leah, for your very kind introduction. I am Lethy Jagadamma from the School of Physics and Astronomy, University of St Andrews. So I will be talking about halide perovskite indoor photovoltaics and how can they be used for developing an eco-friendly Internet of Things technology. So I would like to start my presentation by acknowledging my group members who have contributed to this work, and my collaborators and senior mentors, and also my research funders. And now coming to the topic of my presentation, what is IoT and why it is so important? So IoT refers to a rapidly growing network of internet-connected electronic and electrical devices which can communicate each other and respond rapidly. So this IoT is expected to bring huge impact in many of the technological fields such as industry, agriculture, healthcare sector, education sector, etc. And many of these huge impacts are well aligned with different sustainable development goals as set forward by UN. So incorporation of IoT with the industry is expected to bring a fourth industrial revolution, which is known as Industry 4, through digitization and complete automation of the manufacturing process. Almost 25% more efficiency enhancement is expected. And incorporation of IoT to agriculture is expected to bring optimization in the process of irrigation. So this is made possible by coordinating the ground humidity data with that of weather forecast, and thus IoT helps save a lot of water. This is particularly important because 70% of the fresh water is being used for irrigation purposes. And coming to their application in the building, by incorporating IoT into a normal building, we can convert it into a smart and energy-saving building. The application of this IoT in a building is particularly interesting for our group, and that's one of the research area that our group is focusing on. Why this is so important is buildings are the largest consumers of primary energy, consuming 40% of it, and the building processes account for almost 30% of total carbon dioxide emission. And a recent study has shown that by incorporating IoT into a building energy system, almost 40 to 45% of energy saving is possible. So when we are trying to implement this IoT into a building system, one of the most fundamental component is wireless sensors. A smart building will utilize different kinds of sensors such as temperature, proximity, air quality control, occupancy, etc. in order to continuously monitor and optimize the processes inside the building. So it is projected that almost 75 billion objects will be connected to IoT or connected to Internet of Things system by 2025, and half of them will be inside the building. So there is a huge challenge associated with this incorporation of IoT inside the buildings, because there are billions of devices. So that means there will be similar number or more than that of sensors. We need that much number of wireless sensors. So how are we going to power these sensors? Powering them with the grid-connected electricity or battery is not a feasible solution because of the complexity involved in wiring. And with respect to batteries, they need to be replaced often, and that will bring service interruptions. And also at the end, there is going to be disposed to the environment, which will be challenging for environmental issues as well. So that means we need to develop an alternate powering method for powering these wireless sensors. So in our group, we are trying ambient energy harvesting to self-power these sensors, and it is one of the most promising and feasible solution. Inside the buildings, we have different kind of energy freely available. For example, from these artificial indoor lights, from these artificial light sources, such as white LEDs and fluorescent lamp, and the temperature gradient, and this mechanical energy from human activities and from different electrical appliances. And among these, this indoor light harvesting using photovoltaic effect is most promising because of the high power density available inside the building, and it range from 50 to 300 microwatt per centimeter square. And feasible solution to self-power the sensors, because these sensors need only microwatt to milliwatt range of power. And with the emergence of this IoT, this indoor photovoltaic research is also receiving increased attention. So now coming to what is the main difference between, we are familiar with the outdoor solar cells. So that is silicon solar cells that we see on rooftop. We are familiar with those kind of solar cells. But what's the main difference between this indoor photovoltaics and outdoor solar cells? One of the main difference is in their input light spectra or incident light spectra. In the case of outdoor solar cells, the incident light is from sunlight, which is, we call it the one sun or AM 1.5G, and this spectra extends from UV to the infrared range. Whereas in the case of these indoor light sources, the spectral range is in the visible range. In addition to this spectral range difference, these spectra are also different. They are also different in intensity. The outdoor sun is 100 milliwatt per centimeter square in intensity, whereas in the case of these indoor light sources, they are almost 100 to 1,000 times lower in intensity compared to outdoor sun spectra. So that means when we design different devices, we have to be careful about this intensity differences and spectral differences, and we need to make the adjustment both in the materials as well as device architecture. So these differences in spectra brings additional requirements of band gap. So theoretically, it is calculated that for maximizing the indoor light harvesting, the optimized band gap is around 2 eV, around 1.9 eV, and the efficiency with the optimized structure and incident light with optimized material and device architecture, and the efficiency can reach more than 50%. So among the various photovoltaic materials available today, these halide perovskite semiconductors are particularly interesting and most promising for this indoor light harvesting because of their excellent light to electricity conversion properties and their some band gap tunability. They are easily solution processable, and so scalability is good, and they have got excellent optoelectronic properties such as high light absorption coefficient, as well as charge carrier mobility is much higher. And these materials have already demonstrated a certified power conversion efficiency of more than 25% under one sun illumination. So in our energy harvesting research group, our research is, one part of research is focused on how to, on this indoor photovoltaics of these halide perovskites, how can we enhance their efficiency, how can we enhance their device stability, and also in understanding their device physics. So today I will be talking about one such aspect which is related to the hysteresis effect in halide perovskite photovoltaic devices. So hysteresis refers to the situation in which the JV curve follow the different shape or different directions depending upon the voltage scan, whether it is forward scan or reverse voltage scan, and also depending upon the voltage range we apply and with what voltage step, the JV curves show different shape. It means different shape means it will be showing different power conversion efficiency values depending upon or voltage step or the voltage scan range. So this is a huge issue when we going to power the sensors, because we don't know what's the reliable efficiency. So we need to have devices with the no hysteresis effect or with the minimized hysteresis effect. This hysteresis effect in halide perovskite solar cells has been widely studied under one sun, and it has been discussed that different 4 main reasons are this ionic migration, polarization properties due to ferroelectricity in some of the perovskites, and their defects at the bulk or at the interfaces causing this charge trapping and heat trapping issues and any capacitive effects. But we don't know what is the role of hysteresis in indoor photovoltaic. What happens to this hysteresis issue when we coming to this indoor light harvesting? Because now the spectra is different and the light intensity is different. So how this hysteresis issue is going to affect this indoor photovoltaics? So that was the topic of our research. And we have previous studies under one sun has shown that this device architecture, type of halide perovskites, and the measurement conditions all can influence this hysteresis properties. So in this presentation, I will be showing only the study that we focused on device architecture. However, we have done the other two as well. And in now coming to the different device architectures we have selected, with the two well-known or the two dominant device architectures that we use in halide perovskite photovoltaics is the PAN and NIP. In PAN structure, the ITO electrode collects holes, and in NIP, the ITO electrode collects electrons. And in both device architectures, we selected the methyl ammonium lead iodide as the active layer. And here it shows the JV curve of the devices under one sun and indoor illumination. Here we can see that in one sun illumination, the power conversion efficiency of both NIP and PAN architecture is quite similar, close to 12%. But we can see that the PAN device structure has no hysteresis or very less hysteresis compared to NIP. NIP devices shows higher hysteresis. But we come to the indoor application, indoor JV curves, we can PAN devices shows high power conversion efficiency of more than 30%, and it is the same for both forward and reverse scan with a less hysteresis effect. Whereas in the case of this NIP devices, we see large deviation in efficiency obtained for forward scan and reverse scan. That means these NIP devices shows higher hysteresis effect. Also, if we compare if we compare both one sun and indoor JV curve, we can see that the PAN devices consistently show less hysteresis effect and high power conversion efficiency, whereas these NIP devices show hysteresis and it gets enhanced under the indoor illumination. And this is a summary of average hysteresis indices of more than 30 devices that we have fabricated. And here it summarizes for this is for one sun illumination, and this is for white LED illumination under indoor conditions. Here we can see that the PAN devices consistently show less hysteresis effect under both illumination, whereas the NIP devices show higher hysteresis effect and it increases under the indoor illumination. And we estimated or we characterized this hysteresis effect by using the maximum power point tracking method. So this efficiency is the most reliable efficiency that's coming out of a solar photovoltaic device, and it will be the condition under which these photovoltaic devices will be deployed in real applications. So here we can see that from the MBPT measurements, both NIP and PAN efficiency that we get from MBPT measurements is quite similar, almost 12%, and it is similar to what we got from JV curves. But the main difference is here is that the PAN devices, the efficiency stabilizes quite quickly, whereas in the case of NIP devices, these the stabilization time taken is quite long. This stabilization time indicate the presence of ionic migration in NIP devices. And if we consider similar maximum power point tracking power conversion efficiency in both NIP and PAN devices under indoor light, we can see that again the PAN devices shows consistently high power conversion efficiency above 30%, and it corresponds to output electrical power of 96 microwatt per centimeter square, and it is quite useful to power the IoT wireless sensors. Whereas if we look into the NIP devices, we can see that the efficiency is only below 15%, and this is when we compare the efficiency JV curve value we have seen from the JV curve under reverse scan, these devices showed efficiency of 28%, and that was not the actual efficiency from the devices. So this in deployable or under real conditions, these devices will only show less than 15% efficiency. So from our comparison between the two device architectures, our study showed that these PAN devices between the two structures we have selected, the PAN devices are more promising for indoor light harvesting and for powering the sensors because of their less hysteresis effect and their high power conversion efficiency. Whereas in the case of NIP devices, they suffer from high hysteresis effect and it gets enhanced under indoor lighting conditions. So from the study, we observed that under the indoor lighting condition, especially for devices with the hysteresis effect, always the power conversion efficiency estimated from the maximum power point tracking method should be prioritized over their JV scan measurement, because the JV scan measurements will not give you the reliable efficiency values when the devices have hysteresis effect. So in order to understand what will be the reasons for why these NIP devices are showing better efficiency values compared to the PAN devices, we have done some light intensity dependent characterization of this open circuit and fill factor. So this corresponds to for this VOC versus light intensity plot shows one for PAN and NIP devices. We can see these characterizations revealed that these PAN devices shows less recombination losses, less non-radiative recombination losses compared to the NIP, or NIP devices suffers higher trap-assisted recombination losses. And this is further evident from their variation of fill factor with respect to light intensity. So fill factor is a measure of their collection efficiency as a function of light. So we can see that for the NIP devices under low intensity, the efficiency drops the collection efficiency drops very quickly. So this implies that for the NIP devices at the barriers, there exists a charge collection barrier, especially at the low intensity. When then some traps are present, as we have seen from this plot, this trap effect will be more pronounced under low intensity because the charge carrier, because of the intensity is less, the incident light intensity is less, so the generated charge carrier is also less, and the trap effect will be pronounced, making the barrier at the barrier for their extraction. So to summarize, so our study has shown that this halide perovskite indoor photovoltaics are promising for powering the Internet of Things wireless sensors. And between the two device architectures we have seen that the PAN device structure with the organic charge transport layers are promising because of their high power conversion efficiency and less hysteresis effect compared to the conventional metal oxide based NIP devices. We have repeated that these devices with the TiO2 as well to see the same observation. And also we have observed that for halide perovskite based indoor photovoltaic devices, when there is hysteresis effect, this power conversion efficiency from maximum power point tracking should be always prioritized over the JV curve measurement, because they will not be reliable when the devices have this hysteresis. So that's all from me. Thank you so much for listening. If you have any questions, I'm happy to answer.
Wonderful talk. That's great. I think you're really, I guess, demonstrating the versatility of solar PV. I guess like that, and that different applications it could be applied to. So that was really interesting. I know, like some of the JV curves as well you presented were really beautiful to see. Like the above 80% fill factor was great. I think I'll kick things off with a couple questions. I guess like that.
Sure.
So the PIN type devices, I guess they're the ones generating very quite impressive efficiencies, above 30%.
Yes.
So for indoor lighting. I guess one question around perovskites is generally is about stability and stuff like that, I guess. So I think I saw your devices going up to about 200 seconds. I guess I got so.
Yes. So
I was going to ask how far would you push that, I guess, and if it was long term stable at 30% efficient, is that a commercializable target, I guess, for this?
So regarding the efficiency, regarding the stability, Liam. So this I have shown only for 30 seconds. Of course, this will run for hours, but these when we keep them under low humidity conditions, they are quite stable, because these devices are not encapsulated, so they are quite stable for at least for now. We can say these devices once we have encapsulated and keep inside the glove box, they are stable for more than a year. But when they are keeping in air, so I believe the efficiency will drop. From our stability characterization so far, they have shown within a month they will come there without any encapsulation. Within a month they will come to their efficiency drop down to 60%. So yes, of course, that's why one aspect of our research is to efficiency enhancement through both interlayer modification and also through robust encapsulation methods.
Okay. Oh, that's good to know. I think it's quite an exciting area, I guess, like that, and it's I guess big question of encapsulation, I guess, like that, things like that. I guess we'll see. I guess another question I've got as well is just maybe a little bit general, but the PIN type structure seemed quite complex, I guess, compared to the NIP. There was a lot of layers involved. I guess so I wonder if, for people who maybe don't know that much about device fabrication, could you maybe just talk about the device architecture and how the physical, the kind of human element of developing them, I guess, because it can be quite a complicated process, I guess.
So I will bring this slide. So yes, of course, it is very clear if we compare this PIN and NIP, there are more layers. So one reason here it is this poly TPD, we are using this as the whole transport layer. Without this PFN layer, there is a wettability issue. The methyl ammonium lead iodide will not spread properly on top of poly TPD. So this PFN layer is to increase the wettability. That is only a very 1 nanometer, or that's a very like self-assembled monolayer like structure. So it's very thin layer just to increase the wettability. And here CP layer is there to reduce the voltage step, to make it more ohmic here, and to reduce the voltage drop at the PCBM silver connection. So that is why there are more layers. But here we don't need the tin oxide is quite wettable. The methyl ammonium lead iodide precursor spreads very nicely on tin oxide. So this is a standard structure. That's why we need more layers in PIN, because organic layers, there is some hydrophobic issue on solution processing.
Okay, that's great. Thank you, Leffie, for that. I guess one final question, again, it's slightly general, I guess, but I guess it's just comparing them with silicon PV, I guess, like that. And I guess there's also a few other emerging technologies such as organic dye sensitized. I guess, do you view all these things as competing with traditional silicon and with each other, or is it the market potentially big enough to take them all in, essentially? Think of a better phrase.
Okay, thank you, Leah, for coming. So have you completed, Liam? Sorry, I interrupted.
Oh yeah, no, I was just asking about, is the market
Okay.
big enough to,
Okay.
to allow for all these emerging technologies essentially? And
Okay, so definitely when focusing on this indoor photovoltaic application, definitely silicon is not an ideal option because of this band gap, because the silicon band gap lies here, and they are quite good for one sun harvesting, but not for indoor one. Under indoor, their efficiency is around between 5 and 10%. So they have a limitation because of their band gap. So under indoor photovoltaic, silicon is not the promising material because we need band gap tunable. OPVs are promising, but their cost is an issue because these materials are very expensive. The most of the organic, high efficient organic polymer materials for photovoltaic applications are very expensive. That's why one of the advantage with this perovskite, because of their low cost and solution processibility. Now coming to the dye sensitized, yes, they are very good for indoor light harvesting, but they're also the problem is with their structure, mostly using this spiro kind of structure and this high processing temperature and electrolyte. So that's the main challenge with the dye sensitized, but they have already shown more than 30% as well under indoor light, around 35%, 36%. And the market is quite big because this is going to be, now it is expected that in 2025 it will be going to be a $1.6 trillion industry. So the market is quite big for IoT. So yes.
Okay, right. Thanks very much, Lethe. Actually, thanks for answering all the questions.
So I will stop sharing screen now.
Okay, thanks, Lethe. Okay, so I think from here I'll introduce our next speaker, Dr. Sebastian Sprick from the University of Strathclyde. So just a quick bio of Sebastian. So he obtained his PhD from the University of Manchester under the supervision of Professor Michael Turner. And there he worked on N-heterocyclic palladium carbene catalyst for polytriarylamine syntheses. Then moved to the University of Liverpool and worked with Professor Andrew Cooper developing soluble conjugated microporous polymers, or PINs, as they're often known, and polymers for photocatalysts for water splitting. And then in 2015, he became the research lead within that group. And he was leading the photocatalysis research. And more recently, in 2020, he joined the University of Strathclyde as a Chancellor's Fellow. And today he'll be speaking to us about some of his research in solar fuels, including polymer photocatalysts for hydrogen evolution from water and carbon dioxide reduction. So thanks. Over to Sebastian. Thanks.
Thanks very much, Liam, for the introduction. And should also thank the organizers for allowing me to share the research we've been doing over the last, I think, 6 years or so now, on hydrogen production and carbon dioxide reduction. All right, we start off with hydrogen production from water. The idea being very simple. We want to split water into its components, oxygen and hydrogen. So like, I guess, similar to photosynthesis, where plants use sunlight to convert carbon dioxide and water into sugar. So we store solar energy into chemical energy. So water splitting, doing the same thing as well, splitting water into hydrogen and oxygen, storing solar energy and chemical energy. And then sort of the simplest model, what we can envisage is just using the sun, irradiating a big pot of water with our catalyst in there and splitting water then into its components, of course. That is, of course, also much easier said than just done. The problem is that the mechanism is rather complex, and some of the components requirements that you fulfill are rather difficult to achieve, of course. So we need materials that absorb light, so we go from a ground state to an excited state. Then the exons that we generate need to be separated into charge carriers. And then these charge carriers also have to migrate to the surface to active sites, typically metals, where we do the proton reduction as well as water oxidation. The transport or the migration, we lose a lot of charge carriers to recombination. And then the other challenge as well is the sort of band gap requirements, being able to match the required energies for hydrogen production and water oxidation. Of course, as such, the field is not entirely new. It's been really studied since the 1970s or so. First off, using TiO2, titanium dioxide, but then other sort of materials came in over the years. So particularly more complex oxides have really risen to sort of success, and the sort of metal organic complex has been really active as well. So in terms of the state of the art, this is probably still one of the best systems out there. A system reported now in 2016, so 5 years ago now, by Dorman's group, where they have an efficiency of 1% solid hydrogen. This means they are able to convert 1% of the solar energy that hits the material into hydrogen gas. The system here is rather complex, using 2 components and a gold interlayer, but again, it shows the potential for this, but there's still room for improvement. As I said, 1% efficiency is really far off from what we need to achieve. And that's why there was interest in these organic materials. This really started out in 2009 with this publication by Chin Wang's group on carbon nitride. And over the years, there's been sort of like materials been developed that relate to carbon nitride. And then also other groups sort of came in reporting materials which are more like conjugated polymers. There have been sort of more and more materials been published in recent years as well. The interest in using polymers over inorganic systems is quite simple. It's sort of the argument of tunability. Of course, we want to be able to match the absorption of our photocatalyst with the solar spectrum as much as possible. And you can see here, of course, really want to hit the visible light region. With inorganic materials is somewhat challenging, and the sort of idea of tunability really comes in there. Changing the building blocks of a conjugated polymers allows us to match it much, much better. And also there's the advantage potentially of low temperature synthesis. We can do reactions at much lower temperature, so we are able to produce materials with a sort of smaller carbon footprint effectively. This was really our starting point as well. We had some experience in making these conjugated microporous polymers, so they combine conjugation, but they also don't pack well in the solid states. They have internal porosity, and we had the idea with this material here, by incorporating more and more pyrene. As you go from the left to the right, you can see the colors change. We also shift the absorption onset from really in the blue more and more into the red, and sort of like shows the sort of power of this approach. Really, just changing building blocks really changes the optical properties very efficiently. And this was also our first go, really. And then these materials were tested for hydrogen production from water. I should say we used a scavenger, so we only do the half reaction where we produce hydrogen and oxidize this diethylamine instead of water. But it's sort of like a way forward here in exploring the performance of these systems. By using this tuning approach, also we were able to find materials that are much more active. We went from this blue absorbed material here all the way up to this top material before we saw a drop off, and really shows the power, like tuning, finding the best material in this case here. This has then led to really a large area of research within the group in Liverpool, and like really sort of focusing on designing and understanding these materials. And really sort of we were able to really understand some of the factors really well as well. We understand really well how light absorption and driving force affects the efficiency, how changes in sort of spacing and in the structures that affect driving force affect the production efficiency, how crystallinity matters, how materials are different in their ability to generate charges, how that affects the efficiency, how wettability matters, porosity, particle sizes, and conjugation length. And really sort of like quite a fun area, and we really sort of gained a lot of understanding and being quite able to systematically tune the properties and sort of tuning the properties that matter, and then therefore the efficiency also. But of course, it sort of raised the question, well, so what? It's really similar to inorganic systems as well. And that brought us sort of like to an area how we can distinguish ourselves from inorganic systems, and sort of the area of solution processibility. All the materials on the previous slides, they were all insoluble materials, but we know in organic chemistry, if we include these side chains here, we can make materials are able to dissolve in organic solvents. So we can use this material, we can make this material, and then we can dissolve it in a solvent. In this case here, it's chloroform, and then we can use that to cast films at low temperature. Really, it's room temperature. So
Want to share
and
screen?
that's really an advantage for us compared to inorganic systems. We explored this really quite extensively, and I'll skip ahead for a few years here effectively as well. For materials that are much more active in the end. And you can see even here on the solar radiation coming, hydrogen gas coming off the surface of the material. And this is really quite important in terms of scale up, because that's really the key challenge. To explore this a bit, we looked at scaling up a reactor by covering glass wool with this pool catalyst and just leaving it out in sort of solar irradiation in the UK, of course, so not being particularly sunny. But then over time, as light hits our photocatalyst, we start to see more and more gas being produced, and then it goes off this tube here into the cylinder. You can see over time gas being sort of collected in the cylinder, and we can really now produce significant amounts of hydrogen over time. And again, this is sort of like a very distinct distinction from inorganic systems being able to process materials at low temperature into films, which links up to printing, roll-to-roll printing, like newspaper printing type things, so that really are scalable. Then we would be able to make devices on much larger scale as well. So like, given the size of the problem, being an efficient approach, really. All right, that was really just to give you a taste of the research in this area. The sort of other area, also working at Strathclyde, is looking at carbon dioxide reduction. The sort of fundamentals are actually quite similar as well. Again, we have materials that we need that have band gaps. They absorb light, we create charges, excitons. We need to separate the charges into individual charge carriers. On one side, we ideally, again, oxidize water into oxygen. And then on the other side, we use these electrons to reduce carbon dioxide, potentially into a large range of products. But all of these products will have some use. The key challenge here is that we have two processes happening at the same time potentially. We can see that we get CO2 coming in here. We can do the CO2 reduction. But of course, on the other side, we can also have protons coming in here as well, which we then reduce into hydrogen. And it's really sort of a question of managing the sort of right balance here, being able to do mainly CO2 reduction over hydrogen production. Having said this, of course, mixtures of of carbon monoxide, for example, with hydrogen have potential value as well. But as I see it, really want to drive, ideally, a highly selective system towards CO2 reduction into value-added products. And that's sort of like what we do in the end is really having a similar setup as well. We use water as scavenger again, and organic solvents, which really help with these systems. CO2 is then used as the inert gas, so to speak, in the reduction process. And this was really sort of where we started as well, looking at different systems. We started off actually looking at other systems that contained residual palladium in the system, but we found actually that the selectivity of these systems is really, really poor for for CO2 reduction over hydrogen production. And that's why we sort of changed tack a bit as well, and looking at other reactions to make more selective systems that avoid having palladium present in them. And this is sort of like one of these examples. In this case, we looked at so-called covalent organic frameworks. These can be made using low temperature condensation reactions. You can see here this sort of condensation reaction between this aldehyde and this alpha cyanol compound, producing a link between the two units, and then it sort of can condense into a larger structure of increasing complexity, really. These materials are formed in sort of really high crystallinity as well, as you can see here at the bottom from the XRD spectra. So they have some order to them as well. And then sort of looking at the models here, you can see that we have a sort of stacking of layers, which really agrees quite well as well with crystallinity here, with the sort of XRDs here as well. As I said, these systems, we were really keen on avoiding having palladium present in the system. That's why we used this condensation reaction, but we would need something else to actually facilitate the CO2 reduction in the end. So we loaded onto these systems some rhenium complexes that are able to ligate to this BP ligands instead. Also, it allows us really to selectively load the systems rather than the palladium chemistry. After the loading, we can see we still have really defined XRD patterns here. And again, the models really indicate that we have sort of layered A stacking type materials. These materials then are highly porous. They sort of really show a large uptake of nitrogen, a large step here, which indicates microporosity, and sort of pore width as well really matches onto what we expect from the XRD patterns. And looking at sort of EDX mapping, we can also see that, well, the elements are there, of course, as you expect as building blocks in the material itself, but also the rhenium really remains quite evenly distributed throughout the system. So we don't really get too much detachment or sort of aggregation of rhenium. It seems like it's somewhat a complex formed in the solid state, effectively. This was also confirmed via IR. And then we can see from the V spectra, these systems have really also broad visible light response as well. So they're really able to harvest visible light efficiently. I said already, they are porous to nitrogen, but I guess more crucially, they also are porous to carbon dioxide. They show a distinct uptake of carbon dioxide, even at higher temperature. So we think there's some synergy from this as well, that carbon dioxide is able to penetrate into the material, potentially enhancing the sort of the number of active sites that are exposed. In terms of performance, these systems then perform really well. And it's important here to compare the sort of network material to the actual sort of small molecule analog. The small molecule analog really has initially really high performance, but it also decomposes really rapidly. So after a few hours' time, it is actually inactive. And this is really a known thing in literature as well. For our network material, because we're able to sort of distribute the rhenium centers within the material, we're able to really protect the material, these sort of active sites much more. We can see we have much more steady carbon monoxide evolution over time in these materials. The materials also produce a small amount of hydrogen, but really it's really not a lot, and much less also than the systems that we looked at first, sort of previous first generation materials that were containing palladium, which really produced large amounts of hydrogen. With that, come to my summary. I just hopefully have given you some sort of flavor of some of the research we've been doing in looking at materials for hydrogen production. Really sort of like a quite extensive area of research in this area that we've pursued there. And as I said, the key thing for me is really that we can distinguish ourselves from inorganic systems by making solid materials into active films. I really see this as sort of the way forward as well in this field, being able to move away from suspension systems to printable systems that can really be used on large scale. And I also showed you some of the work we're doing on carbon dioxide reduction into chemical feedstocks. It's a really challenging area, quite exciting for science, but even like producing carbon monoxide from carbon dioxide is already quite exciting, actually, because we use carbon monoxide, of course, on really large scales. And the way we produce it currently is really one of these sort of larger greenhouse gas emitters. In terms of acknowledgements, of course, there are a lot of people I need to thank, people in Liverpool and police or the full catalysis group, both of the students that did the work, of course, and many of these projects were really highly collaborative as well. Lots of collaborators as well really play a crucial role in these projects. And then these guys for funding, also enabling some of the sort of work with these collaborators and visits. And with that, I would like to thank you for your attention and, of course, happy to answer any questions you might have.
It's such a hot topic at the minute, hydrogen production, things like that. So it's nice to get like a bit of flavour of some of the science you're doing behind it as well. Sure. I guess it's now carbon capture and utilization, I guess, not just storage. So I guess it's nice hearing aspects of that as well, how you can actually get rid of the CO2 and make useful building blocks.
No, sure, absolutely. I mean, like, as I indicated already, sort of like, even production of carbon monoxide is like one of the challenges really that we face. Syngas is so important, and we really need to find green routes to make syngas. Why not use some of the waste streams that we have?
Yeah, absolutely. Okay, we've got a couple of questions in the chat, I guess. So one from Anna Marie. I guess, so what are the efficiencies you're expecting to achieve for hydrogen production with this process, or what would be an acceptable rate for the process to be feasible? I guess I'm guessing large scale.
That's $1 million question, isn't it? Really. I mean, like, so the Americans, they American Energy Agency sort of touts around 10% to be necessary. But I don't know. I go to energy meetings and you hear all different numbers being thrown around. The honest answer is we're not really sure right now what's needed. But it seems probably 10% or more. Yes.
Okay, thank you. And we got another question from Letty. I guess, what is the theoretical maximum efficiency of these conjugated polymer-based photocatalysts?
In terms of conversion efficiencies?
I guess, yeah. So I guess it could maybe tie into the amount of like 1.5 G or lithium.
Yes. I've got no straight answer for you there, but like I think sort of the what I've seen reported as sort of like, because of the band gap requirement as well, of course you need to be able to have not only 1.23 electron volt sort of band gap, but also the driving force for that as well. So like the maximum some people sort of say is like around like 18 to 20% possibly. So like we need to reach pretty high numbers and closer to the sort of limits as well to really potentially be having products that be useful in the future.
Okay. Oh, thanks for that. I guess I've got one question as well, and I guess it's maybe just tied into like morphology of the kind of devices and how you cast them. I guess there's it, and I guess also the reproducibility of the polymers. I guess it looked relatively simple, the polymer for the hydrogen production. Is it quite reproducible synthesis? And
yes,
I guess do you see much variation with like device to device? I guess I got all.
No, I mean, to be honest, no. From the studies we've done, we don't see much variation between different batches. And like also, I moved from Liverpool here, reproducing results here now. We've been actually quite successful as well. There seems to be very little variation in that. The materials are really straightforward materials. They have low complexity. It's like you couple some things together, you purify them, and they are the same. That's a beauty of organic chemistry again. It's really reproducible. I don't know, like one thing that we were really concerned about was sort of molecular weight effects and these sort of things as well, but they don't seem to be super important as well. Actually, having relatively low molecular weights already sort of leads to high activity already. It seems all fairly reproducible.
Okay, that's good to know. That's great. Okay, so thanks, Seb. That was a great talk. And
thanks very much.
Cheers, thank you. So I guess we'll move on to our penultimate speaker, Johnson Jimba. And so today, Johnson is going to speak to us about flow measurements for carbon capture and storage for transport applications. I think previously Johnson has worked on indigenous solar-powered vehicles as well as energy requirements for CO2-based carbon capture and CO2 based on hydrotossolite absorption technology. Sorry about that, that's a mouthful.
Yeah.
So today we'll be hearing about his exciting PhD work. So thanks, Johnson, over to you. Okay.
Yeah.
Right. Okay. All yours. Thanks.
So, okay. For some reasons, I'm seeing on my screen, so I don't know if I'm good to go now.
Yeah.
Okay, excellent. Thank you very much, and thank you, everybody. Okay, so my name is Johnson, and I'll be giving a very, very short presentation on the work we are doing. For my PhD, basically understanding flow measurement for carbon capture and storage transport applications. So just to give a very, very brief, again, a recap of what we've been hearing, we know that there's a threat that's fundamentally caused by humans' activities on the mother planet. And we know that these activities, mainly spanning from our consumption of energy and production of energy as well, have continually increased the concentration of CO2 in the atmosphere. And as you can see from the chart, you see that the global average annual atmospheric CO2 concentration have reached more than 412 parts per million. As at this is 2020 data, and I guess it's a bit more now. So almost doubling the industrial levels of about just between 180 to 200, to 280 parts per million. So within this period, you will see that CO2 emissions have grown more than fourfold, with over 50% of the cumulative increase observed to be emitted in the last 5 decades. So now, consequently, what are we seeing? So we are seeing that all this growth is leading to severe weather conditions, rise in sea levels, and collapse of our ecosystem. We've been seeing the awful headlines quite recently. So how do we prevent these threats? So it is important that for us to prevent this looming threat, we reach net zero emissions. And we know that CCS is one of the engineering solutions to meet both our near-term and long-term emission reduction targets. So you will see from the little description here, it's just showing the potential of CCS, or what CCS is targeted to achieve now. Nearest decade, that's before 2030, and even in up to 2050. So the target is that CCS is used to capture up to 14 to 15% of our current emissions, and hopefully we will get there. So because we know that CCS has a very, very significant role to play in our emission reduction targets, so we now have to examine the role that CCS metering will be playing and some of the current challenges. So, okay. So first of all, we know that an effective metering of CO2 across the CCS network is a requirement for large-scale adoption of CCS. First, it will help us to improve transparency in doing business in the new model of, in the new CCS industry. So for instance, a 1% accuracy in measuring CO2 will mean that we will have a correct financial settlement among the actors in this industry. Of course, this is what we need to achieve our net-term target. So in terms of custody transfer applications, CCS metering has a significant role to play. And more importantly, in helping the CCS technology to meet all sorts of environmental and regulatory landscape, accurate CCS metering also has a role to play. For example, it's also helping the health and safety of the operations of CCS technology. So, but again, there are challenges. Of course, we know that there are challenges in measuring CO2. It's unlike other conventional fields. So CO2 is supposed to be transported near its critical point. So as a result, there's a liability that CO2 can easily be transitioned from one phase to the other. And this means that most of the available meters are going to struggle in measuring CO2. Again, another challenge is the indicative levels of impurities in CO2, in CO2 stream during CCS operations. So these impurities also potentially affect the behavior or achieving accurate behavior of metering from the stream. So you can see from the little chart I put here, just to demonstrate at what conditions we'll be measuring CO2. Now, we agree that for us to measure CO2, we will, especially at a very large scale, we will either be measuring CO2 in the dense or supercritical phase. There are quite arguments between these two conditions. So, but favorably, we have to measure, we will have to transport CO2 in the dense phase or the supercritical phase. And what this means is that we need to have or assess the current metering technology in terms of being able to accurately measure CO2 at these conditions, the dense and the supercritical condition. So what are the flow measurement technologies that is available? So commonly, we have either voluntary measurement technology or direct measurement technology. So these are the common measuring technology in the oil and gas industry, because of course that's the starting point. So we have the likes of differential pressure meters, we have electromagnetic and radiation technologies. We also have direct mass flow measurement technologies, so just like the Coriolis flow meter, the thermal mass meter, and other kind of measuring technology, the turbine meters, tomography, vortex flow meter, etc. So, but our work, the essence is that we assess each of these candidates meter and see how well they will perform. So what we decided to do is to start with Coriolis meter, because of course it has been used widely in the oil and gas industry. So we feel that it's going to be a good place to start for a number of reasons. Of course, one, because it has the potential to directly measure mass flow, and again, it's usually not affected by the property of the fluid. So you can see that it's rarely affected by density variation. And reasonably, Coriolis meter is also able, to a reasonable extent, measure CO2 is measured CO2 at multi phase conditions, and they also have great potential to function under subsea application. So now, flow measurement requirements. So there are a range of requirements in terms of CCS application. So what are the maximum permissible error that's expected or are required for flow meters to be acceptable in CCS applications? So for now, most of these requirements are based on what we have in the EU UK emission trading system. So the requirements are fundamentally based on the requirements given by the EU UK emission trading systems. We also have other organizations like the US National Institute of Standards and Technology. We have the EU Measurement Instrument Directive that also stipulated their own requirements. However, most of the baseline MPE is what we have or what is being defined in the EU ETS. And you can see there's just a little summary of the requirements we have according to these organizations. So we can see that of the EU UK ETS. Their recent conclusion is that the maximum permissible error that we're expecting from meters is for mass CO2 transfer is plus or minus 2.5%. Whereas most other organizations are quite stricter. So in terms of giving a definition a bit lower than the 2.5 given, which is about 1.5. However, most of these organizations want, in particular, meters to functions. The meter performance that is expected. The performance that is expected from these meters are usually in the range of 1 to 1.5%. So that means our assessment will be based on this MPE, 1 to 1.5%. So what's the aim of our study? Potentially, our aim is to improve our understanding of flow measurement for CCS transport applications so that uncertainties can be reduced to stay within the requirements of EU ETS. And our core objectives is to assess Coriolis meter. Is to assess Coriolis meter first, and then subsequently assess other kinds of meters that we think is going to be very, very relevant in CO2 flow measurement. So what we did is to measure CO2 at condition relevant to CCS operations. So like I stated earlier, the dense phase, the supercritical phase, and maybe the liquid vapor two-phase conditions. Of course, this is not the condition we want, but things happen and we could have two-phase conditions. So we want to see if how well or what the behavior of this meter will be at these conditions. Again, also one of the later work we're also planning to do is also measure CO2 under two-phase conditions, or other when it's at a condition that reflect the practical CO2 stream. So that means we also consider some range of impurities. So what are our methods? So basically we are designing a rig. Based on the gravimetric principle. So what do I mean by gravimetric principle? So what we are doing is that we are trying to flow a conditioned CO2. So we condition CO2 and then we flow the CO2 through the meter we are testing, the meter on that test, and then take the weight, the measurement of the CO2. Then we compare the weight, the total, the weight of this CO2 and the totalized mass flow from the meter itself. So that's basically how we intend to do our work. So if you look at the rig we have, fundamentally the main components we have here are just the pump. So because we need to get a pump compression system that's able to vary the condition of CO2 at both dense and supercritical conditions. The meter itself, like I say, is just Coriolis flow meter that we are testing. And we have some couple of valves. So like we have solenoid valves that will help us automate the system, because the system works using a start and stop approach. So we need to be able to dynamically operate the rig itself. Then we also have a back pressure controller here. You will see our back pressure controller. So the back pressure controller is to help us maintain the upstream pressure that we are running, through which the system is running. So in a way, the back pressure controller's unit will help us to maintain this pressure and prevent some sort of flashing, which is possible, especially when you're operating at dense phase condition. Okay, so just a bit more on the explanation of the rig itself. So we have two major loops in the rig. So the first loop is the conditioning loop. So the conditioning loop, as you can see, is just, we have it, this is our CO2. We have a heat exchanger around the CO2 where we can use to raise or decrease the temperature as we want. And then the conditioning loop is, what we first do is we pump this, using this pump, we pump the temperature, we pump the CO2 through the meter itself and back to the first cylinder. So in this way, we want to achieve equilibrium in the CO2. So when we condition the CO2, we want to first study the condition of the CO2 to see if we are operating at the condition that we want to flow the CO2. So, and now the flow measurement system itself, the flow measurement run itself. So what we do is, we have this our CO2, like I say, we condition the CO2, then we pump the CO2. Using this pump, we pump the CO2 through the meter itself and back to another store. So this is the we have this is the feed cylinder, this is the store cylinder. So we pump the CO2 from the feed cylinder using the pump through the meter itself and down to the store cylinder. So like I said, this is the back pressure controller. So the back pressure controller helps us to maintain the pressure at which this pump is pumping the conditioned CO2. So we pump from the feed cylinder through the meter itself and then down to the stored cylinder. So there's a weight scale here. So that help us take the reading of the weight of the CO2 that's pumped in the stored cylinder. Then we compare it to the totalized mass flow that we recover from the Coriolis meter itself. So then we compare these. So this is just the simple operations we undergo in running the rig. So this is the rig we've designed already. We've designed the rig itself, so you can see the Coriolis meter. The Coriolis meter is just It's a 1-inch coriolis meter, although running through a 1/4-inch pipe. So there's a reducer wediment that help us to match the size of the coriolis meter through the lines that we have. So this is the we have the a dampener, that is the position dampener. So the position dampener help us to smoothing the flow of the CO2 that we have because of the kind of pump we are using. So this is the feed cylinder, the stock cylinder, and the feed cylinder. You will see we have a heat exchanger around the feed cylinder that help us vary the temperature that we want to run the system. And then we have our data acquisition and unit, where we take the pressure, the flow, and the pressure, the flow, and other secondary parameters that we need in running the rig itself. So the rig that we design is just basically up to 100 bar, because what we need to do, we need to just run the system at supercritical condition, at dense and supercritical condition, basically. And what that means is that we are trying to run this system up to pressure as high as 80, 85, 75, no, above the supercritical point, because the critical point of CO2 is 73 bar. So we want to run above the above the critical point, which is 75, 85, etc., and temperature above 31 degrees. So that's why we're able to run the system above 31 degrees. And then the flow rate we could achieve is just a little above 90 kilogram per hour. So this is the meter itself, the meter we're using. So the result we have so far in our baseline measurement error that we've got so far, starting from the supercritical conditions. So it's quite interesting, the result we have for the supercritical condition, which we haven't had, there haven't been any tests on the supercritical phase of CO2. So the measurement result, I mean, the performance of coriolis meter at this condition was a bit strange, in that we have error as high as 2 to 3%, 2 to 3%, which is kind of strange. And we feel this was, of course, we did this we were very careful. We did that, we run that again and again, but we keep having the same. So a number of things came to our head. Possibly we were considering maybe we have to carry out a temperature correction of the meter, which does not seem that there's need to do that, because the meter itself has a default temperature correction. So, but yes, this needs to be further investigated, which we will do before we can conclude that the meter is have a staggering behavior in accurately measuring CO2 at supercritical condition. However, for the dense phase condition, we have a very, very brilliant performance. So the meter handle the flow very brilliantly. So we have our errors way below 0.5, way below 0.5. Then for the two-phase, of course, we expect to have a very staggering result. But for the gas phase, just in confirmation of what we have in the existing result, we have.
Hi, Johnson.
Hi.
Sorry to interrupt. Just to keep an eye on time, essentially.
Okay.
Perhaps. Sorry to interrupt. But yeah.
All right. Thank you. So what am I trying to say here? I mean, overall. So you can see that from what we have here, supercritical conditions, we have our maximum permissible error to be a bit higher than what the requirements of the EU UK ETS. This needs to be investigated further before we can think of applying some kind of corrections. For the dense phase, we have a very, very brilliant result. The meter performance was excellent. For the two phase, it's of course, it's as expected. We know that many meters we struggle in accurately measuring CO2 at two-phase condition. But for the liquid and the gas condition, we also have a very brilliant result. So in conclusion, we're able to develop our gravimetric flow rig and evaluate the performance of one of the candidate flow meters. So the rig has been validated, and the flow measurement experiment were conducted on the Coriolis flow meter under the conditions that are representative of CCS transport operation. So like I said, the performance of Coriolis meter under the dense phase condition were excellent, which complementing the existing performance we have that have been reported in previous studies. However, their performance under two-phase and supercritical conditions were staggering. So like I said, this needs to be further investigated, especially for the supercritical conditions. So the future work that we are planning basically is to run future experiments that will cover CO2 mixtures that mimic CO2 stream in practical CCS system. So we've defined the mixture. So we try to have a chat with some of the operators, transport operators, to see what they want, what they will allow to run through their pipelines, and we've gathered a composition. So this is what we hope to be running in the nearest phase of our experiment. So most importantly, I would like to thank Energy Technology Partnership and the TUV SUD for their collaboration with Herotwat in funding and supervising and the project. Thank you very much. Thank you everybody for your attention.
Okay, thanks a lot, Johnson. That was a great talk, and it's really quite interesting to see the techniques involved with carbon capture and storage and things like that. I think just for the interest of time, we might just move straight on to the next speaker. But Johnson, we'll be hanging around the networking here after this, so please go and talk to him, learn a bit more about his work, and ask him any questions. So sorry about that, Johnson, but I think just for the interest of time, we'll need to move to the next speaker. So our next talk is Ahmed Mohammed. So he's joining us from slightly further afield, which is Queen's University, Belfast. So as far as the ETP is concerned, that makes an international talk. So welcome, Ahmed. I'm very happy you could join us. So Ahmed will be speaking to about his PhD work and the impact of residential batteries on low voltage networks with PV and EV. So thanks, Ahmed. Over to you.
Thanks, Liam, for the introduction. Just confirming that you can see my presentation and that you can hear me well. So, hello, everyone. I'm a PhD candidate at Queen's University, Belfast, and today I'm introducing our work on the impact of residential batteries on low voltage networks with PV and electric vehicle. I'd like to thank my supervisors, Dr. Robert Press, Dr. Amy Lou, and Professor John Morrow, and all the ETP organizers for organizing such a wonderful event. So actually, this work tackles the rapid deployment of low carbon technologies such as solar photovoltaics and electric vehicles and residential batteries. Customers are getting attracted to these technologies in order to maximize the profits, as well as from a social perspective in order to mitigate the climate change and to have a better impact on the environment. In the literature, we can see a lot of studies that have investigated the impact of solar photovoltaics and electric vehicles, as we all know that electric vehicles represent a high demand, which can form a peaks, and the solar photovoltaics with high penetration can impose some challenges related to the high reverse power flow, which can actually impact the voltage and other power quality issues. However, the impact of high penetrations of residential batteries has not actually considered in the literature extensively. Mainly, the use of batteries is to solve the problems of photovoltaics and electric vehicles. However, with high penetration of these units, supervised coordination is required in order to only maximize the utilization of these units, but also to mitigate their negative impacts, which can occur with high penetrations. That's why this work actually aims to answer this question of what is the impact of autonomous residential batteries deployed on a wide scale for different heuristic operation strategies, and how actually the distribution system operators can maximize utilization of these units in order to mitigate the impact of solar photovoltaics and electric vehicles. This work actually considers both the customers and the distribution system operator benefits by providing a case study implemented on a real low voltage network located in Northern Ireland, and aims to answer the question of how can the residential batteries can be operated to benefit both the customer as well as the DSO with lower cost incentives and complexity. So for the methodology actually starts by having an actually low voltage network, which consists of the specification of the cables and feeder households at each load node, and the distribution of these households on the three phases. Afterwards, we are importing household profiles represented in normal demand profile for 1 year, photovoltaic PV generation, and electric vehicle charging profile. Similarly, for the battery, we are sizing the battery based on commercial practice, and we are developing or generating 1 year power profile for each household under different control strategies. Afterwards, we are performing power flow analysis using unbalanced three-phase backward forward sweeping power flow calculation for 1 year. And at the end, we are analyzing the data and providing the conclusion of our results. So for the batteries, we are operating the battery using 3 strategies. Mainly, the main strategy called ST1, which is the normal strategy, which aims to maximize the PV self-consumption such that the battery is charging whenever the generation exceeds here. The generation of the PV is exceeding the demand, and hence the battery is starting to charge, and it's charging whenever the demand exceeds the generation or exceeds the zero threshold, for example. So here the battery is charging. So this is the conventional threshold method that actually using a power threshold of 0. So it's a charge whenever the generation exceeds the demand, and it's a charge whenever the demand exceeds the generation. The second one aims to actually benefit more the network. For example, the first one may unintentionally or actually mitigate the PV and the high demand for electric vehicle or heat pump using charging and charging. However, it doesn't focus actually on the peak time of the PV or the EV. That's why the second one, actually, we are setting a predefined scheduling period such that the battery is starting to charge from a specific time, for example, from 10 a.m. to 4 p.m. to mitigate the PV during the peak. And similarly for the charging, the battery is starting to charge after 4 p.m., for example. The third one focuses mainly on benefit the distribution system operator by setting the thresholds, scheduling thresholds, such as ST1. In addition, actually, we are setting a thresholds. So, for example, the lower threshold means that the battery will start to charge whenever the generation exceeds the demand by 1.2 or 1 kilowatt, for example. And similarly, it will start to charge when the demand exceeds 2 kilowatt, for example. So all these strategies are or the operation are operating all over the year. However, in the winter, the batteries are being charged also during low time of use tariff during overnight in order to maximize the energy arbitrage. So for the case study, we have an actual low voltage network of 397 meter feeder with 6 nodes, and it has been provided by the distribution network operator of Northern Ireland, which is MIE Networks. And the feeder is a 3-phase for wire and supply 30 households as shown in this figure. So we have obtained 1 year half-hourly energy profiles for 30 houses, and which were obtained actually from the low carbon London dataset, which was provided by UK Power Networks. For the electric vehicle, we are assuming that all the households are having electric vehicles and solar photovoltaics and batteries. So for electric vehicles, we are generating charging patterns for the 3 kilowatt standard charger and the 7 kilowatt fast charger using a probabilistic model. For the PV pattern, we have actually an actual or real profile for 1 year for a household in Northern Ireland, and we have used this one and the scale for each household because they are mainly in the same area, so the generation will be roughly the same. For the results, so after actually performing, after generating different profiles for each strategy, for each battery of household, and sizing the batteries and PV based on commercial practice, after combining all together and bar flow calculation, here are the results. So for the results, we are actually analyzing the results in terms of the voltage, magnitude, the phase loading, and also the voltage imbalance and the losses and the degradation for the batteries, in addition to electricity bill. So for the voltage, this low voltage network is a radial. So surely the farthest node from the network or from the substation will suffer from voltage violations. So due to the high penetration of photovoltaics, we have over voltage events here in blue. So this is before the battery, and the orange here after the battery for first strategy, after the battery for the second strategy, and for the third strategy. For the first strategy, the battery managed actually to mitigate the impact of photovoltaics. However, we can see that we have still over voltage events for the second strategy because we are setting scheduling periods. The over voltage events have been mitigated better than the first strategy. So for the third strategy, actually we can see that the battery solved all the over voltage issues, and that the voltage is below the allowable limits of the UK, which is 252 voltage. And for the line loading, we have observed that the overloading has occurred for phase C, for the first line that connects the substation to the first node. So we can see actually that the first strategy increased the loading on the cable and didn't actually mitigate the overloading. And this is because if we have a lot of batteries are connected to the same network and operating autonomously by charging overnight to maximize the profits, so we are actually forming a new peaks during overnight, during the low time fuse tariff. And hence, actually, the results show that the overloading can increase with high penetration of batteries. For the second strategy, because the batteries are setting a specific threshold for charging, so the battery is focusing on the peaks, and also the battery is not being charged fully every day, and hence it's not being charged during low time fuse tariff frequently, and hence it has mitigated actually the overloading. For the third strategy, we can see a much better enhancement, because we are setting a threshold for discharging and charging, and hence for discharging the battery is integrating more to mitigate the impact of electric vehicles, for example. And similarly, the battery is not being charged fully using PV, and hence it's not being charged frequently during the overnight. So talking about numbers, ST1 and ST2 decreased these overvoltage events by 52 and 69%, while ST3 managed to solve all these violations for the overvoltage. For the overloading, ST1 didn't mitigate cable overloading, but however, ST3 optimized all events above 80% by 54% compared to ST2, which actually enhanced it by only 18% roughly. For the voltage imbalance, the results show that the autonomous operation of low-carbon technology and batteries may unintentionally improve the voltage imbalance across the nodes. However, in some cases, the high penetration of these technologies may worsen the voltage imbalance, as can be seen in Figure 5, and hence need to be monitored. However, we didn't observe any violations or breach in the voltage imbalance. In terms of integration of low-carbon technologies such as electric vehicles and solar photovoltaics will increase the losses actually in post-phase and neutral. The results for this case study, the losses has increased in phases by 60% and 117% in the neutral. And the presence of batteries can slightly reduce the losses for the second and by. However, for the first strategy, as we can see here, the losses has increased, and this is because this strategy doesn't focus on the peak, and also besides the frequent charging of the first strategy during the low time fuse tariff. In terms of degradation and annual electricity bill, the best customer profitability can be achieved with ST1, because ST1 is mainly focusing on benefiting the customers, as the electricity bill increased on average by 5% and 15% for ST2 and ST3. And hence, the distribution system operator should compensate for this loss in profitability for a return of supporting the network by operating their units using, for example, ST2 and ST3. Regarding the degradation, the best degradation was for ST3 because it's not being used frequently. However, for ST1, the batteries are degrading faster because they are being using frequently all over the year. For ST2, it's balanced the degradation, and hence, for example, in this we are analyzing the degradation throughout the 10 years, and we can see that the average loss in BSC's capacity throughout the 10 years operation of all households is 5.3% for ST3, which actually can prolong the lifespan of the battery to be operated for longer than 10 years. To summarize, for the first strategy and second strategy and third strategy, in terms of overvoltage or voltage events, the third strategy managed to solve 100%, while second strategy only 69%, and first strategy 52%. Regarding the overloading event, the first strategy actually increased the overloading events by 20%, while ST2 and ST3 managed to solve and mitigate these events. For ST3, the better improvement was achieved by 84%. For phase losses reduction, the first strategy worsened the losses, while the second and third strategy managed to mitigate or to reduce the losses in post-phase and neutral, while ST3 is much better than ST1 and ST2. For the degradation, the best degradation achieved using the third strategy, while for the electricity bill reduction was achieved for the first strategy because it's mainly focuses on customers' profitability. Hence, to conclude, this research work showed that the integration of low carbon technologies on low voltage network will lead to different challenges that should be handled by the distribution system operator. Relying on residential batteries to mitigate these challenges is very attractive, which you can actually avoid or defer the need for conventional reinforcement, such as upgrading transformers, cables, or adding reactive part compensators, and so on. However, residential batteries should be managed properly, and supervised management is required, especially on wide scale. And this can actually be achieved unsophisticatedly by operating residential batteries to benefit both the network and customers using, for example, ST3, while the customer should be compensated for the loss in their profits. And hence, incentive schemes should include network losses and battery degradation because, for example, operating the battery using ST3 will prolong the lifespan of the battery compared to ST1 and has better impact on the losses, and this should be monetized in the incentive scheme. And the distribution system operators should introduce attractive incentives to encourage customers to install these units to benefit the network through proper utilization. And as I have mentioned, this will help mitigating the negative impacts of low carbon technologies on the network and may avoid or defer the need for augmentation, as well as reducing or preventing the curtailment associated with PV overgeneration or high demand. For future work, we are going to investigate smart and practical incentive schemes and policies that should be applied in the case of residential batteries. So at the end, I would like to thank you for listening, and I like to acknowledge the funding of SPIRE2 project, as this work is part of SPIRE2 project, supported by the European Union's INTERREGVA program and managed by the special EU programs body. There's a full paper of this research which can be accessed from this link and has been published on the site, the last edition. And there is also a free tool that can be used to generate battery control profiles, which has been actually used in this research work and can be accessed from this link. Thank you.
Thank you, Ahmed. That was a wonderful talk. I think it was great to hear some of the stuff at the end. I guess linking your practical modeling calculations to like policy recommendations and things like that, I think is a really important area. And I think to try and get the full systems integration and stuff like that is really important. So it was great. So I guess one question for me, so I think with the housing, was it modeled on, I guess, detached houses just from the image and stuff like that? And I guess just how robust is it, I guess, if you switched it to like a tenement flat and stuff like that? Is it much tweaking involved, or is it pretty straightforward, I guess, to analyze that going from like site to site, I guess, to
so you mean that the household profiles?
I guess so. From my understanding, the modeling was, I guess it was based on, so you had a series of 6 houses, I guess, from your images that were, hypothetically given out X amount toward EV and taken in from PV, I guess. But if you were to vary that to like tenement flats and stuff like that, would it make any difference?
Yes, so it was mainly, we have a low voltage network with 30 households, mainly distributed like 6 households per each node. And due to the limitation of the available data and the privacy of accessing the actual demand of these households, so we have used from open.set by UK Power Networks different household profiles for the same category. And we have distributed these households randomly. For electric vehicle profiles, we have distributed the electric vehicles, assuming that 50-50% based on the zip map statistics, that the chargers are mainly 50% in households, 3 kilowatt standard and 7 kilowatt fast chargers. And we have also distributed these or assigned for each household randomly. And we have used a probabilistic model to generate the electric vehicle pattern. For the PV generation, we have used an actual real profile pattern for a household in Northern Ireland, and we have scaled this profile for each household based on the commercial recommendation of a PV size for each household, which can be calculated using the demand of this household, for example. Actually, more underlying technical details can be accessed in the papers. So,
yeah. No, thanks. I'll scope that. It was thanks for sharing the link in the paper at the end as well. It was good to see the full detail. I guess a couple of questions that came through in the chat. I know we're a wee bit over, but so what type of batteries were used in your investigation, and do your results depend on the type of batteries that considered? I guess.
Not really, actually, because we are using a model to model the battery operation, which is actually based on the round trip efficiency, the bar conversion system efficiency, which is the inverter, for example, and the state of charge limits and the depth of discharge. And these generally actually can be assigned. These are generic models that can be used for different types of batteries. However, as we are here talking about residential batteries, so most of the batteries in the market are lithium-ion batteries, and most of the people are actually deploying lithium-ion batteries with a high round-trip efficiency. So our work actually was to obtain these data from the market, available lithium batteries in the market. And so we are using, for example, the round-trip efficiency of the Sonnen battery, which is around 87%. Similarly, the inverter efficiency is around 90%. So we can obtain the total efficiency of our system or our batteries using these data, which can be accessed easily using the data sheets of different manufacturers. But generally, we have used lithium-ion batteries, but the model is capable to actually accommodate different other types of batteries.
Okay, thanks, Ahmed. And I think we've got one more question, if you don't mind. So do you think there will be a consideration that these batteries would be included as part of the service by the energy provider? And I guess the comment that this might save the consumer from having to invest in initial capital cost, I guess.
Okay, yeah, we were actually investigating some of these. So this is one of the incentives plans. So for example, Northern Power Grid has introduced a project called Distributed Solar Study, which was to deploy Moyaxa batteries on a residential low voltage network. And they were actually, at the end, the economic model showed that the batteries, and also our result is showing that the batteries is not an attractive for customers because of their high capital costs. However, with some incentives, the batteries can be profitable and can break even. But these costs actually will depend on whether these batteries are going to provide services to the network operator or not. So, for example, the Northern Power Grid showed that the battery can actually be controlled according to the DSO preference in return for incentives. So these incentives can be whether it's like an initial capital payment in order to help in the initial capital cost, and therefore it will mitigate the costs and it will at the end achieve a profitable investment, or it will be an annual payment for 10 years of operation, and hence it will also mitigate and it will help customers to deploy these units. However, under these incentive schemes, the battery will be mainly operated according to distribution network preference, and hence whether using a direct signal from the DSO to operate the battery, or using specific thresholds or scheduling or predefined scheduling periods. So in our work, actually, in order to overcome the complexity of sending a direct signal to specific customers and the need of the complex smart meters, for example, to apply these signals, by actually assigning predefined scheduling periods based on the season, whether it's winter or summer, and based on the low voltage problems, whether they are having a high demand and high overloading, or they are having over voltage, for example, problems. So hence they can specify the scheduling periods and the threshold in which the battery should charge or discharge.
Okay, thanks a lot, Ahmed. Yeah, that was quite comprehensive. So yeah, thank you for that overview at the end there.
Thank you.
I think we've run over a wee bit, so I'll close the session here. So again, I'd just like to thank all the speakers for really interesting talks, and just the attendees as well for coming along. I just encourage everyone, I do go check out the posters this afternoon. A few of the PhD students have put up some good posters, so go check them out and talk to the students. And yeah, the presenters will be around after this session, and so go talk to them and just introduce yourself, network a wee bit, and things like that. And finally, I'd just like to thank Jose and the technical staff behind the scenes for helping out with everything. Okay, so yeah, do enjoy the rest of the day, and yeah, thanks for attending. Okay, cheers.